A Brief History of Time, written by Stephen Hawking, read by Akashveer. This is chapter number 7. Black Holes Ain't So Black. Before 1970, my research on general relativity had concentrated mainly on the question of whether or not there had been a Big Bang singularity. However, one evening in November that year, shortly after the birth of my daughter, Lucy, I started to think about black holes as I was getting into bed. My disability makes this rather a slow process, so I had plenty of time. At that date, there was no precise definition of which points in space lay inside of the black hole and which lay outside. I had already discussed with Roger Penrose the idea of defining a black hole as the set of events from which it was not possible to escape to a large distance, which is now the generally accepted definition. It means that the boundary of a black hole, the event horizon, is formed by the paths in space-time of rays of light that just fail to get away from the black holes, hovering forever just on the edge. It is a bit like running away from the police and just managing to keep one step ahead but not being able to get clear away. Suddenly I realized that the paths of these light rays could never approach one another. If they did, they must eventually run into one another. It would be like meeting someone else running away from a police in the opposite direction. You would both be caught, or in this case, fall into the black hole. But these light rays were swallowed up by the black hole. Then they could not have been on the boundary of the black hole. So the path of light in the event horizon had always be moving parallel to or away from each other. Another way of seeing this is that the event horizon, the boundary of a black hole, is like the edge of a shadow, the shadow of impending doom. If you look at the shadow cast by a source at a great distance, such as the sun, you find that the rays of light in the edge are not approaching each other. If the rays of light that form the event horizon, the boundary of the black hole, can never approach each other, the area of the event horizon might stay the same or increase with time, but it could never decrease, because that would mean that at least some of the rays of light in the boundary would have to be approaching each other. In fact, the area would increase whenever matter or radiation fell into the black hole, or if two black holes collided and merged together to form a single black hole, the area of the event horizon of the final black hole would be greater or equal to the sum of areas of event horizons of the original black hole. This non-decreasing property of the event horizon's area placed an important restriction on the possible behavior of black holes. I was so excited with my discovery that I did not get much sleep that night. The next day I rang up Roger Penrose. He agreed with me. I think in fact that he had been aware of this property of the area. However, he had been using a slightly different definition of a black hole. He had not realized that the boundaries of a black hole according to the two definitions would be the same, and hence so would their areas, provided the black holes had settled down to a state in which it was not changing with time. The non-decreasing behavior of a black hole's area was very reminiscent of the behaviors of physical quantity called entropy, which measures the degree of disorder of a system. It is a matter of common experience that disorder will tend to increase if things are left to themselves. One has only to stop making repairs around the house to see that. One can create order out of disorder. For example, one can paint the house, but that requires expenditure of effort or energy, and so decreases the amount of ordered energy available. A precise statement of this idea is known as the second law of thermodynamics. It states that the entropy of an isolated system always increases, and that when two systems are joined together, the entropy of the combined system is greater than the sum of the entropies of the individual systems. For example, consider a system of gas molecules in a box. The molecules can be thought of as little billiard balls continually colliding with each other and bouncing off the walls of the box. The higher the temperature of the gas, the faster the molecules move, and so the more frequently and harder they collide with the walls of the box, and the greater the outward pressure they exert on the walls. Suppose that initially the molecules are all confined to the left-hand side of the box by a partition. If the partition is then removed, the molecules will tend to spread out and occupy both halves of box. At some later time, they could be by chance all be in the right half or back in the left half, but it is overwhelmingly more probable that there will be roughly equal numbers in the two halves. Such a state is less ordered or more disordered than the original state in which all the molecules were in one half. One therefore says that the entropy of the gas has gone up. Similarly, suppose one starts with two boxes, one containing oxygen molecules and the other containing nitrogen molecules. If one joins the boxes together and removes the intervening wall, the oxygen and nitrogen molecules will start to mix. At a later time, the most probable state would be a fairly uniform mixture of oxygen and nitrogen molecules throughout the two boxes. This state would be less ordered and hence have more entropy than the initial state of two separate boxes. The second law of thermodynamics has a rather different status than that of other laws of science, such as Newton's laws of gravity, for example, because it does not hold anyways. Just in the vast majority of cases, the probability of all the gas molecules in the first box being found in one half of the box at the later time in many millions of millions to one, but it can happen. However, if one has a black hole around, one seems to be a rather easier way of violating the second law. Just throw some matter with a lot of entropy, such as a box of gas, down the black hole. The total entropy of the matter outside the black hole would go down. One could of course still say that the total entropy, including the entropy inside the black hole, not gone down. But since there is no way to look inside the black hole, we cannot see how much entropy the matter inside it has. It would be nice then if there was some feature of the black hole by which observers outside the black hole could tell its entropy, and which would increase whenever matter and carrying entropy fell into the black hole. Following the discovery described above, that the area of the event horizon increased whenever matter fell into a black hole, a research student at Princeton named Jacob Bekenstein suggested that the area of the event horizon was a measure of the entropy of the black hole. As matter carrying entropy fell into a black hole, the area of its event horizon would go up, so that the sum of the entropy of matter outside black hole and the area of the event horizon would never go down. This suggestion seemed to prevent the second law of thermodynamics from being violated in most situations. However, there was one fatal flaw. If a black hole has entropy, then it ought also have a temperature. But a body with a particular temperature must emit radiation at a certain rate. It's a matter of common experience that if one heats a poker in a fire, it glows red hot and emits radiation. But bodies at lower temperature emit radiations too. One just does not normally notice it because the amount is fairly small. This radiation is required in order to prevent violation of the second law. So, black holes ought to emit radiation. But by their very definition, black holes are objects that are not supposed to emit anything. It therefore seemed that the area of event horizon of a black hole could not be regarded as its entropy. In 1972, I wrote a paper with Brandon Carter and an American colleague, Jim Bardeen, in which we pointed out that although there were many similarities between entropy and the area of event horizon, there was this apparently fatal difficulty. I must admit that in writing this paper I was motivated partly by irritation with Bekenstein who I felt had misused my discovery of the increase of the area of event horizon. However, it turned out in the end that he was basically correct, though in a manner he had certainly not expected. In September 1973, while I was visiting Moscow, I discussed black holes with two leading Soviet experts, Yakov Zeldovich and Alexander Storbinsky. They convinced me that according to quantum mechanical uncertainty principle, rotating black holes should create and emit particles. I believed their arguments on physical grounds, but I did not like the mathematical way in which they calculated the emission. I therefore set about devising a better mathematical treatment, which I described at an informal seminar in Oxford at the end of November 1973. At that time, I had not done the calculations to find out how much would actually be emitted. I was expecting to discover just the radiation that Zeldovich and Starobinsky had predicted from rotating black holes. However, when I did calculations, I found to my surprise and annoyance that even non-rotating black holes should apparently create and emit particles at a steady rate. At first, I thought that this emission indicated that one of the approximations I had used was not valid. I was afraid that if Bekenstein found out about it, he would use it as a further argument to support his idea about the entropy of black holes, which I still did not like. However, the more I thought about it, the more it seemed that the approximations really ought to hold. But what finally convinced me that the emission was real was the spectrum of the emitted particles was exactly that which would emitted by the black body, and that a black hole was emitting particles at exactly the correct rate to prevent violations of the second law. Since then, the calculations have been repeated in a number of different forums by other people. They all confirmed that a black hole ought to emit particles and radiations as if it were a hot body or a black hot body with a temperature that depends only on black hole's mass. The higher the mass, the lower the temperature. How is it possible that a black hole appears to emit particles when we know that nothing can escape from within its event horizon? The answer, quantum theory tells us, is the particles do not come from within the black hole but from the empty space just outside the black hole's event horizon. We can understand this in the following way. What we think of an empty space cannot be completely empty, because that would mean that all the fields such as the gravitational and the electromagnetic fields would have to be exactly zero. However, the value of the field and its rate of changing with time are likely the position and velocity of a particle. The uncertainty principle implies that the more accurately one knows one of its quantities, the less accurately one knows the other. So, in empty space, the field cannot be fixed at exactly zero, because then it would have both a precise value and a precise rate of change, both zero. There must be a certain minimum amount of uncertainty or quantum fluctuations in the value of the field. One can think of these fluctuations as pairs of particles of light or gravity that appear together at some time, move apart and then come together again and annihilate each other. These particles are virtual particles, like the particles that carry the gravitational force of Sun. Unlike real particles, they cannot be observed directly with a particle detector. However, their indirect effects, such as the small changes in the energy of electrons orbiting atoms, can be measured and agree with the theoretical predictions to a remarkable degree of accuracy. The uncertainty principle also predicts that there will be similar virtual pairs of matter particles, such as electrons or quarks. In this case, however, one member of the pair will be a particle and the other an antiparticle. The antiparticle of light and gravity are same as the particles. The other half of this chapter would be in the second part.